initially I was not liking DOE that much, and how I started learning it. So that also I'll share it with you, and then we'll also understand the concept of blocking in the experiment. Then in that we are going to see like randomized block design RBD, balance incomplete block design, that is BIBD. Now here I'll not be talking much on a theory part, so we'll just touch upon the intuition, like what is those concepts, and then we'll jump into the use cases, that is example. And in example we are going to see three types of example: factorial design, randomized block design, and BIBD. And then there will be a question and answer as usual, and then we'll sum up the session. So let us start with the introduction part of this DOE. So in that, I would like to share my story. So I was, the person who is not liking the DOE when I was in second semester. So after, but this when this was a subject at that time, I was not liking this subject. Can you please mute microphone? जिनका चालू है वो? Okay. I was literally, irritated at that time because I was not able to understand the terminology and, its meaning. Like there are three basic key elements, you can say: randomization, replication, and blocking. So these are the key elements of DOE, but I was not able to understand all these things. At that time, all seems to be, like messy and confusing. And I was literally irritated. Like it is, shown in this picture. That was, you can understand. This is my picture. At that time, I was not having any picture, otherwise it would be quite similar to this. That was my situation, because what my habit is, I used to understand with the visualization means I just try to visualize the concepts. So whatever concepts that I'm learning, that I'm in back of mind, I used to visualize those things, and then I'm making an imaginary drawing. But that I was failed to do that. And then like what to do, that was the confusion. And then one day in a winter season, I was taking bath in my hostel. I used to stay at Vidyanagar in my hostel, so I was taking a bath over there. And actually I was struggling to get optimum warm water, because in in my hostel we have two taps. Like this one is for the hot water and cold water. Now I was struggling to get, because if I run only this step, then I'll be getting very hot water, which is I cannot take a bath by using that water. If I use this water like from this cold, that is also not feasible to take a bath in a winter. But I need to optimize, like some of the water from here, some of the water from here, and the optimum output I should get so that I can take a bath. Now I struggle to adjust all those points, like इसको थोड़ा सा खोला, इसको थोड़ा सा खोला, and then वो बैलेंस नहीं बना, फिर इसको थोड़ा सा ज्यादा खोला तो फिर वो ज्यादा गर्म हो गया, तो फिर इसको थोड़ा सा ज्यादा खोल दिया. So likewise I was adjusting and struggling with getting the optimum warm water so that I can take a relaxed bath. Now after few days of struggle, I was able to get the correct opening position, like ये कितना खोलना है, ये कितना खोलना है, right? So that I was get that position, and I just tried to repeating all these things कि भाई अभी इतना ये hot water का इतना ही खोलना है, और cold water का जो tap है उसको इतना ही खोलना है. And then I was getting a immediately like whatever warm water that I need to take a bath. Now by doing all this exercise, at that time I was not able to understand, like this is a super case of a DOE, design of experiment, that I used to study in the lecture. But then when I attended the lecture, I was able to correlate the same situation in DOE lecture. Like how? Let me explain. So there are two factors I was having. One is hot water tap and cold water tap. So this is factor 1, this is factor 2. There are 4 levels. You can consider these are as a level. So these are the levels, like, so these are the opening position. मैं इसको कितना turn करता हूँ. So you can consider इसको मैं ये center position पे रखता हूँ कि this is the first point, this is second, third and fourth. इसको अगर मैंने fourth पे ले गया तो it will be full open. And if it is at third, then you can say 75% open, likewise that. So both the tapes are having 4 levels. and the response variable. So what is my output that I'm finding out? So that is my warm water. Kitna degree hona chahiye? Now in that case I was not measuring the degree, but that should be, let's say, 39 to 40 degrees of Celsius, ताकि वो हम उसको बाथ में यूज कर सके. So that is the optimum water that we were looking. इससे ज्यादा भी नहीं चाहिए था, इससे कम भी नहीं चाहिए था. So बहुत बार हमारा जो रिस्पॉन्स वेरिएबल होता है, ठीक है, उसके भी हम उसको कैटेगराइज करते हैं कि बहुत सारे केस में हायर इज बेटर, बहुत सारे केसेस में लोअर इज बेटर, बहुत सारे केसेस में ऑप्टिमम इज द बेटर. सो लेट्स से इफ वी आर टॉकिंग अबाउट द yield, देन हायर इज, मेजॉरिटी ऑफ द केसेस में हायर इज बेटर होता है. If we are talking about the rejection or the failure or the defects, at that time lower is always better. But in this kind of situation, let's say some range is given like 39 to 40 degrees, so that optimum level is important for us. So we should get our output within that range. Otherwise, if it is, let's say, below that or above that, then it is a difficult, or that is not acceptable to the customer. Now here in this case, I was the customer and I was the experimenter. And like if you arrange this, then it is a 2:4 design, right? So in that way, you can consider like this is how this warm water theory that is I just given the name warm water theory, but that is how I understood this DOE. And then my interest was at the top, you can say, like in DOE. I was very much curious. So बहुत सारी चीजें शायद अगर सिलेबस में नहीं है लेकिन बुक में लिखी है, then also I at that time I used to read all those things to for a my curiosity कि ये इसमें क्या होता है, इसमें क्या होगा. So likewise I started studying that. But unfortunately, when I was working at that time, I was not get a chance to experiment this in a real life situation much more detail, right? So एक दो प्रोजेक्ट्स किए हैं, बट जितने सिक्स सिग्मा के जो प्रोजेक्ट्स मुझे मतलब इतनी अपॉर्चुनिटीज मिली थी उतनी इसकी नहीं मिली है. So whatever I had learned during the practical situation, that also during the session I'll be sharing with you. Now, in statistics, we used to give a definition that it is a science of collecting, analyzing, and drawing conclusion from the data. Now, here the most important part is data. Now, how this data is collected? So there are several ways. So mainly there are three ways. The first way is to collect data from the observational study. So we are observing something, and then we are collecting a data. And then there is a survey that we can conduct, and then we can get the data. So that is second method. And the third method is a experiment. So where we have some set of input and set of output, and then some controllable, uncontrollable parameters and all. And then we conduct some experiment and get the output. And those experiment is recorded properly. Like what was the level of factor one? What was the that is the input level of factors. So that is all we used to monitor systematically, and then it is nothing but a data, right? So now here we are going to talk about this experimentation aspect. So these are all the important aspects, but here for this session, we are going to talk about the experiments and its outcome and how can we analyze those data. Now let us look at what do we mean by the DOE. So this is the standard definition that I got from some article. So design of experiment is defined as a branch of applied statistics that deal with the planning. So it includes the planning. When we talk, when we call this term as a DOE, then it is not only the experimentation. It is also include the planning, then conducting. So once the planning has been done, you have to conduct the experiment. Once these experiments are conducted, then you have to analyze the result. And then once it is analysis is done, you have to interpret the result. Right now, about what? So here, if we read this entire definition like this, DOE is defined as a branch of applied statistics that deals with the planning, conducting, analyzing, and interpreting the controlled test. Now, this controlled tests are nothing but the experiments to evaluate the factors, right? So, factors is nothing but your input variable that control the value of parameters. Now, here parameter, this is some standard definition. That is why they use the term called parameter. So, I didn't change the definition, right? So, here the parameter is nothing but your response, or you can say y, or you can say your output variable, right? So or it may be more than one. So let's say yield is one of the y, and let's say rejection level is, let's say, another y. So here it will be y1, here it will be y2. So likewise, it can be group of parameters. So basically, this definition is telling that, whatever we are conducting an experiment, that is controlled test. So we want to collect the data, we want to plan those experiments, we want to analyze those experiments, and let us have an interpretation of those analysis that we perform, that what factor or which factors that are controlling the value of our y or the response variable. So that is the concept of DOE. Now, if we put this definition with reference to any working environment or real environment, then in real environment there is a process, right? Now, process is what? So it takes some of the inputs, so it may be controllable, right? So one part is controllable inputs. Now here, when we talk about this input in real life situation, it may be with reference to material, with reference to, let's say, men, with reference to, let's say, methods, with reference to, let's say, uh, machines, with reference to, let's say, process parameter. So it may be anything, right? So that you can control. So I can, decide which method to use. I can select the machine on which machine this process will be performed. I can decide the process parameter, like what will be the temperature, what will be the pressure, what will be the speed. So that all I can control. So these are all the controllable inputs. So this all will be part of the process. That process is taking as an input. There are several uncontrollable inputs are also there, right? So what could be that? So it can be, let's say, ambient temperature. That is not in your control, right? Yes, in some of the cases, up to some extent, if you are having that facility, like in laboratory, they are maintaining the ambient temperature at some degree. So in that case, up to some extent you can do, but in real life situation where this workshop is there, workshop in the sense like the shop floor I'm talking about, in the company. So in that you can't control that, or you have some limitation of controlling them. So that is ambient temperature, humidity. It's a mood of the person, the person who is performing that process. Now you can control the person, that it should be done by person A, but what is the mood of person A, that you can control, right? So these are all the uncontrollable inputs, you can say. Let's say power fluctuation, that you can't control, or let's say power cut, that you can't control, because it is some external factors that is affecting to the process. And ultimately, after taking this input, both controllable and uncontrollable input, the process is delivering some output, right? So that is the how this process is performing. Now here, what is our aim when we talk about this DOE at that time? And this is the it is also known as a turtle diagram, right? Now here, this diagram will be useful in many situations. So whenever you are also understanding this QMS, quality management system, in that also similar type of diagram is explained. But let us understand this diagram with reference to this DOE. So here, we want to get the optimum level of these inputs. So controllable inputs जो भी है हमारे, उसका optimum level क्या है? What should be the speed so that my output will be on a higher side? Like let's say if I'm talking about here yield, then higher is better. So to increase the yield, what should be the optimum level of temperature? What should be the optimum level of the speed? What should be the optimum level of, let's say, pressure? Right. So whatever parameters are there, what is the optimum level? What is the optimum level of recipe? Recipe means how you are mixing the material. That is, there is a huge scope of the DOE. So I used to work in a ceramic industry. So when I was working with previous companies, I used to go as a consultant. So they are also using the recipe. Recipe means it is a mixture of different types of material. Now, in which proportion it needs to be mixed, that is the key for that company's success. वो आगे जाके लोट एक्सेप्ट होगा, रिजेक्ट होगा, टाइल्स अच्छी बनेगी, अच्छी नहीं बनेगी, that all depend upon the recipe. So there is a huge scope of the DOE, and what they are doing is they are doing trial and error, that kind of thing, right? So that trial and error, ultimately in experiment also we are doing trial and error, but it is in a systematic way that we are doing. So that is some scientifically proven theories that we are using to conduct those experiments, and what they are doing. So based on their experience, they are conducting the experiment. So that is, some cost part is there. And when you go to the industry at that time, cost part will be always there. So if you suggest like 2 days to this, and then you are conducting this, like that, what you can say, you want to conduct an experiment, then they will not give you a straight away permission. It is not as simple as that, because with each experiment there is some cost associated with it. So we need to, best possible way that we have to design, so that they will be, give you a permission to conduct the experiment. So cost will be less, and within the less trial and error, you will be able to give them a right combination or combination, out of this process as possible. Now here also you can, imagine your warm water theory, right? So like in this process also you can, think that warm water theory. Now, why this experimentation is needed? So now experiment is having, many purposes. Now, what are those purposes? So let us have a look at some of the main purpose of the experiments. So determine cause of the variation. So from where the cause, like this variation is coming. So if we conduct some systematic experiments, then we can be able to do that. And if we determine this, cause of variation, then it will be very easy to control them, because variation is always, it is inversely proportionate to the profit, or you can say to the efficiency, to the productivity. As your variation is increasing, all your efficiency and then all will be getting down, right? So that is the relationship between them. So it is always better to have a less variation. Now, another purpose of conducting an experiment is finding the condition which maximize or minimize the response. So as I explained that, many of the cases we want to maximize the response. In some of the cases we want to minimize the response. In some of the cases we would like to optimize the response, right? So optimize means at some level, right? Now, the third purpose of the experimentation could be comparing the response between two different settings of controllable variable. So let's say if I'm having, let's say if I'm, keeping speed as, let's say 100, and I'm having also a choice of, let's say 150, and temperature I'm having, let's say 280 degree, and let's say here it is 300 degree. And then let's say pressure is, let's say here it is 150 and here it is 200. Now I would like to understand that if I, run this combination, like when I keep the speed like that, these are all the controllable variables. So if I, keep at this level, then what would be my, you can say, this value of the response variable. And we would like to compare these values, like when it is at 100, then what is the value? When it is 150, then what is the value? So that is what we want to, compare. And another purpose could be like obtain the model which can predict the future responses. So ultimately, why we are developing a model, or why we are doing this experimentation. So let's say if we have, known that speed and temperature and this pressure should be at this level, so that it can give a best result. Now we would like to predict the future response. So that is the ultimate purpose of an experiment, or the model building. Now let us have a just quick look at the history of DOE. So currently DOE is used in different fields. So it may be engineering design, it may be quality improvement, it may be industrial research, manufacturing, physical and biological science, social science, even in psychology it is also used, business management and marketing research. Everywhere it is used, right? Now if you, look at the roots of it, then roots of this modern experiments, right, that are stem from the R.A. Fisher's work that he did in agriculture experimentation in England. So initially, this DOE concept was applied to this agriculture field, and then it was adopted by all these industries by, doing some, modification, and some of the things are as it is, and likewise it was evolved. Now, some of the important definitions that we should look at. So let's say, what do we mean by the experiment or the run? So an action in which experimenter changes at least one variable and observe the effect. So one variable, that is what? It may be our factor, right? So at least one of the factor we are changing, and then we are observing the effect of changing them, right? So that is called as experiment. Then what do we mean by the experimental unit? So it is the item under study upon which something is changed. So ये effect कहाँ पे हम measure कर रहे हैं? So that is in the experimental unit. So it can be material, it can be product, it can be human. Now I'll share one experience that I had in one of the plastic industry. So they are basically that granules that they are using, and they are making some plastic parts out of that. Now those plastic parts are this is made in injection molding machine. Now in that injection molding machine, they have to add some material, that is the granules, that is इतने छोटे छोटे दाने होते हैं जो granules के plastic के वो होते हैं, and then it is melted. Once it is melted, इसमें बहुत सारे process parameters लगते हैं, that is more than 40 parameters that they are setting. But out of that, let's say by brainstorming and discussion, we came up to, let's say, 10 different parameters, like what would be the pressure 1, pressure 2, and pressure 3. There are three different types of pressure. Then speed also, let's say, two types of speed. So speed 1, speed 2, all are different level, right? And then there is another it's cooling time, right? So all those parameters were there. So now to find out the best combination, and all are at two levels, so 2 raised to 10 design was there. So in that, what we did is, so we applied the Taguchi method. One senior faculty was there with me, so he was having quite experience of this Taguchi implementation, Taguchi experiment implementation. So in that, now what is the experiment? So we have given them a plan, like first experiment. So that is, let's say, speed 1, speed 2, then pressure 1, pressure 2, pressure 3, cooling time, and so on. There are so many, you can say, this factors. Now here it should be at, let's say, low level, it should be at high level, low level, high level, and all this low and high were defined by conducting the brainstorming and the historical data that they are having. Now here in this case, they are making this kind of plastic part that is having some design, right? So this kind of plastic part were there. So that part is nothing but the experimental unit for us. Because what we are doing is, after running this, we are just inspecting this part, whether it is okay or not okay. Here it is binary, but let's say if you want to make it more elaborative, then if it is okay, then fine. If it is not okay, then how many defects are there? So here it can be n number of defects. So how many defects are there? So that is how we have converted this into the some, you can say, like discrete variable, like there is some numbers are there that we can consider for the analysis. So we can measure the DPU, defect per unit. So in this, let's say two defects are there. The second experiment we run, and then we have obtained some of these things, and then we have observed some of the DPUs and all. So that is what the experimental unit in this experiment. The third is like independent variable. So as I was talking about this experiment, so this speed, pressure, cooling time, temperature, all these things are nothing but the independent variable, or you can say it is a factor. Now it is one of the variable under the study that is being controlled at or the near to the target. Now there is some requirement, like what should be the speed. So they have defined that speed should be, let's say, between 150 to 170, right? So that is what they had defined, and it should be maintained between this. And now in that we have to uh, make the level like low level and high level. So it should be maintained at that level when we are conducting an experiment. And now its levels needs to be changed systematically. So here when we I can't just like that I can take this 150 as a low level and 117 as a let's say high level. So it needs to be systematically and after taking their input, because see here only our statistical knowledge will not work, because along with that we have to add their like practical this experience plus you can say business domain knowledge or the technical knowledge, that also we have to take into account so that it will be a more optimum design. So that is what the independent variable in this case. What do we mean by the dependent variable? So response or target variable, you can say that is the dependent variable. It is the characteristics of the experimental unit, you can say. So here we have understood what is experimental unit, and out of that, let's say experimental unit, as I discuss about that plastic part, what we are measuring. So we are measuring the defects, right? So that is one of the characteristics of that. Let's say if it is in a continuous form, then it may be let's say length, it may be let's say diameter, it may be the size, it may be the let's say weight of that part. So it can be anything. So it is in line with what we want to optimize. So that we have to measure, or we have to take as a dependent variable or response variable. And then what do we mean by the effect? So effect is nothing but the change in the response that is caused by change in the factor or the independent variable. So whenever we are making any changes to this independent variable and its label, at that time, what is the change that is observed in a response variable? So that is called effect. So let's say when my temperature was at 150 degree, at that time my DPU was let's say 10, that is 10 defects per unit. And when I increase this to let's say 250 degree, at that time it become let's say 15, right? So DPU will be 15. So this change is nothing but the effect of that change that you can say. Now, what do we mean by the replication? So replication is, two or more experiments conducted with the same setting. So in the first experiment, I had set the value of let's say temperature as 150, and for the speed, let's say 130, and for the pressure, it is let's say 180. So this is the setting level or the experiment that I designed. And here I have run one experiment, so that is a single experiment you can say. But let's say in the same setting, I'm running it for the 3 times. So first, two, and first, second, and third. And whatever result I'm getting, that is I'm noting it down. So let's say in the first run, I have observed that is 8 DPU, then 9 DPU, then 7 DPU, right? So that is what this 1, 2, and 3 is nothing but this replication, right? So that is the replication, and that is needed because in one experiment, if you are getting the best result, then you can't generalize it, right? So it may be due to chance, and we as a statistician, we used to believe that it should be confirmed. So you can also name it as a conformity trial. So once you have found out the best optimum parameter, or let's say you are conducting these experiments, you have developed the design, then you repeat that design if it is feasible in the sense some cost part and some resource part, that all you need to take care while you are conducting the experiment. So if it is feasible, you should always go for the replication, so that you can have a confirm that okay, with this set of let's say parameters, or with this experiment, we can get the optimum result. So that can be finalized, and then in a routine practice that can be followed by the people, so that they can get the optimum result. Now, what do we mean by the blocking in experiment? So this is just we discuss about some of the terminology and the simple definition of the DOE. Now, what do we mean by the blocking? So blocking is, it is a design technique which is used to improve the precision with which comparison among the factors of interest are made. So let's say often, this blocking is used to reduce or eliminate the variability transmitted from the nuisance factor. Here, this nuisance factor, that is the important part, right? Now, what do we mean by the nuisance factors? So nuisance factors are the factors that may influence the experiment. So it may influence the experiment, but we are not directly interested to, study that. Now here, if you remember that warm water theory, in that, let's say, what do we mean by this blocking? Let us try to, correlate these things with that warm water experiment or warm water theory. So let's say in that case, I experimented that all theory in my bathroom, right? So in my room, my bathroom, I did that. But let's say there is one of my friend who is also struggling for that. So let's say in his bathroom, if I go and do the same experiment, right? So there is a room to room or the bathroom to bathroom, whatever, that, wear and tear is there with the tap, right? So that will be there. So that is called nuisance factor. I'm not interested to study, impact of the bathroom to bathroom. What is the variation? That is not I'm interested to study. But that will be there. That impact will be there. So that is a block, right? So if I'm, conducting this experiment in my, 5 friends that room, then let's say there are 5 blocks are there, right? Now, let's say if I, repeat the same experiment in my own bathroom, let's say for the 3 times, that is what? That is replication, right? So that is the difference. You can say what is the difference between this replication and the blocking. Many of the time it may seems confusing, but that is how you can, just separate it out. Now, if we take the example of the blocking, then an experiment in a chemical process may require two batches of raw material, right, to make all the required runs. Now, we are having in one batch which is supplied by supplier one, we can't conduct all these experiments, right? So what we need to do, so like the difference between these batches due to this supplier to supplier variability may be there. So this is from supplier one, this is from supplier two. So there may be chances that there is a difference between this quality and this quality. However, material is same, but it is supplied by different suppliers. So there may be chances that some variability will be there. But we are not interested to study the supplier to supplier variability. So that is not our ultimate objective. But here we have to consider this variability, or we need to eliminate. Basically, this is due to the nuisance factor. So what we need to do, we need to eliminate this from our analysis. But how can we eliminate? So we need to use this concept of blocking. So here, this supplier one, that can be my block one, and the supplier two, that can be my block two. So to eliminate this blocking effect, I have to declare it as a blocking block one and block two, and then I have to design this experiment in such a way that I can have the information about this block also, because in analysis I need to eliminate that. So that is why we have to use this blocking theory. Now, another very important aspect, that is, you can say it is a base of the blocking theory, that a block is set of a relatively homogeneous experimental condition, right? Now, what do we mean by that homogeneous experimental condition? So in this case, in this particular case that we are, taking this example, at that time, we are expecting that, there is a difference between this batch one and batch two, or supplier one and supplier two. That is what we are expecting, and that is why we are keeping it as a block. But for the supplier one, if I take, let's say, 5 sample from this chemical, right? So there are 5 sample I have drawn. So within this 5 sample, the variability will be very less. And here if I take 5 samples, then variability will be less. So that is what the concept of rational subgrouping, or you can say it is a homogeneous experimental condition. So if I use this S1 material, that is supplier one material, then it will be a same across all. It will have the same impact across wherever I am using. Similarly, I am having the assumption with this supplier two. So that is what the base condition for the blocking. So blocking is done in such a way that in one block all the homogeneous things will be considered or assumed. So that is how it is done. Now let us have a intuition of this randomized block design. So RBD. So here in a randomized block design, that is RBD, there is only one primary factor under consideration in an experiment. Similar test subjects are grouped in a block. Each block is tested against all treatment levels of the primary factor at random order, and this is intended to eliminate the possible influence by other, this nuisance factor, or you can say the extraneous factor. So basically, why we are doing this randomized block design? So you can see this is, let's say, block one, block two, block three, and we are having, let's say, 4 different treatments. So treatment A, B, C, and D. So you can see here this treatment B, A, D, and C. So that is randomly assigned in this block. Here you can see this treatment D, C, A, and B. That is also randomly assigned. Here you can see this, D, B, C, and A. That is also randomly assigned. So it is having the block. The design is, randomly assigned to each of the blocks. So that is why it is known as a randomized block design. So that is how it is designed. So I'll not go much in a theory part. So we just wanted to touch upon the intuition part of the RBD. Now, another terminology that we are discussing is balance incomplete block design. So that is BIBD. Now, let's say many of the time we are facing some issues related to the in certain experiments using randomized block design, we may not be able to run all the treatment combination in each block. Now here, if we look at this design, now due to some problem or due to some, let's say, lack of material, I can only run, let's say, three design or three treat. I can apply three treatment in each of the blocks. So here I can't accommodate this, four treatments. So here I need to give only three treatments because I can't spend this much of material in just experimenting, right? So it may be any reason, but I'm just telling you that that management will give you only permission to get only three instead of this four. So in that case, what we need to do, so let's say one thing conventionally we can do is A, B, C. Here also, let's say B, C, A, and here also, let's say C, B, A. That kind of assignment we did, and we forget about the D treatment. But that is not our intention because we want to study that, right? So what we can do out of this four, any three will be randomly assigned to this. Now this three will be assigned in such a way that it should be repeated. The number of time it is repeating, it would be same, right? So let us look at in the slide so that we can understand it in a better way. Now this situation occurs because of, let's say, shortage of experimentation facilities, or you can say the physical size of the block. So let's say in such block we can't do that. For example, when I was discussing with Jyoti madam at that time, she has given an excellent example. Let's say I'm having three sunscreen lotion, right? Now I want to study the impact of that three sunscreen lotion on a human, let's say, chicks. So उनके गाल पर क्या असर आती है, that the researcher wanted to check. Now अभी अपने पास गाल तो सिर्फ दो ही है, लेकिन मेरे पास treatment three है. So that is what physical size of the block is not enough. So in that case, what we need to do? So I have to take, let's say, five people, and in to those five people. So this people one, two, this three, four, and five. And here, let's say A, B, and C. That kind of thing is there. I'm having. So what I need to do? Randomly, I have to assign. So you experiment with this A and C, A and B. This is randomly assigned, something like that. But it should be like when I calculate this, how many time A is repeating. So that should be equal to, like, the number of A is repeating is equal to the number of time the B is repeating, and the number of time this C is repeating. Right. So let us look at the this visualization. So before that, this line, let us have a look at it. So when all the treatment comparisons are equally important, the treatment combination is used in each block should be selected in balanced manner so that any pair of the treatment occurs together the same number of time. That is what I just wanted to convey. Now let us have a postmortem of this terminology, that is BIBD. Let us try to understand this each of the element, that is balanced, incomplete, this block design. So what do we mean by the balance? So each pair of treatments occurs together in a block an equal number of items, equal number of times, right? So each pair of the treatment occurs together in a block an equal number of times. So that is what we are talking about, the balanced part of it. The second thing is incomplete. Not every treatment will appear in every block, because that is why we have went to this BIBD. Otherwise we could have used this RBD. Then block is what? So that is experimental group. Let's say there is the block that we just discussed now, right? So it may be like we want to compare the gender to gender, or let's say block 1 to block 2. That kind of thing is there. And then design. So this is nothing but your experiment that you are going to conduct. So that is what BIBD. Now let us have a look at what is balance and what is imbalance, or you can say what is valid and what is invalid BIBD. So here I'm having, let's say, four treatment 1, 2, 3, and 4. This is my four block 1, 2, 3, and 4. Now here I have randomly assigned some of the treatments. So here T1, 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 and this T2. So that is what I have assigned over here. Here, this T2, T3, T2, T3, likewise it is assigned. And here also it is assigned randomly. Now, if you calculate that how many times this T1 is repeating, so let me just show you some calculation. So here it is 1, 2, 3, 4, 5, and 6. So it is repeating 6 times. Treatment 2, 1, 2, 3. So it is repeating only 3 times. T3, 1, 2, and 3. It is repeating only 3 times. And this is 4 times. Right. So that is what you can say, it is imbalance. There is no balance between this treatment. Actually, it is supposed to be there. So it is a invalid BIBD, you can say. Now, let's say in this situation, you can see this is assigned randomly, but if we have a calculation of it, then it is T1. How many times it is repeating? 4 times. T2, 4 times. T3, 4 times. And T4, 4 times. Right. So here you can see this is T2, 1, 2, this 3, this is 4. Right. 1, then there's 2, 3, and 4. 1, 2, 3, and 4, and remaining 4. Right. So this is how it is, balanced. Now here you might be thinking that it is a kind of a and RBD where all the treatments are there. But let's say if you are eliminating some of the treatments due to some physical constraint, then it becomes a BIBD. So this is invalid. This is valid design, you can say. Now we are going to discuss about some of the use cases of the factorial design. So we are going to take 3 use cases. One is with reference to the factorial design we used to do. Another one is of RBD, and another one is for the BIBD. I'll also share the link to download this PPT and the file, R file, and the data file that I'm going to use in this lecture, so you can download that. Now I'm having one data that is CO emissions. A chemical engineer wanted to study the impact of burning amount of fuel and ethanol amount on the CO, that is carbon monoxide emission released. Now response variable is this CO emission that is measured in a grams per meter cube. Factor A, that is nothing but the amount of ethanol, and factor B, that is nothing but this ratio of this fuel, right? So air to fuel ratio, that is the factor B. And the replication in this experiment is done 2 times, right? So that is what the data is available. Now this data is taken from one book, so I intentionally put the snap of that book. So that book is written in the last reference slide. So you can also do the repeated thing, or you can further study. That is very good book that is available in the library. So here you can see the ethanol additions, that is 0.1, 0.1, 0.1. So this is, let's say, level 1. This 0.2, 0.2, and 0.2, that is level 2. This is, let's say, level 3. So there are, this ethanol is at 3 levels, 0.1, 0.2, and 0.3. Now this B, that is air to fuel ratio, that is also available at the 3 level, that is 14, 15, and 16. So 14, 15, 16, 14, 15, 16, 14, 15, 16. So likewise it is available. Now it is having this 2 replication. So when they conduct the experiment, so at 0.1 and 0.1 and this 1.4, that is 14. So in the first experiment, they have got the result as 66. In the second, it has got the result of 66. Right. So this is, you can say replication 1, replication 2. So that is what it is there. Now, let us go into the R and then, try to understand this by performing that in the R itself. Let me increase the size so that you can easily view this. Now here, there is one package called DAEWR. Now what is the full form? I don't know, but that is a package in which this data is available, and some of the design also we are going to use it from this when we go for the BIBD. So let us load this package. First, you need to install this package as usual. So I hope it is, you are user of R. so you know that. So I'm not explaining those part. Now here there is one file which is CO data. It is exactly the same which I shown you in the this PPT. So it is the same file. This file is already there. So let me load that CO data into DF so that I don't need to write down this CO data over there. And then let us have a look at it. So you can see here how it is arranged. So this is ethanol, then ratio, and then CO, that is carbon monoxide. So this is up to this point, up to this point. Sorry. Yes, up to this point, it is first replication. Now you can observe this. From here again, it is starting with this 0.1 and 14. Here also it is 0.1 and 14. So first, what we had we have got is like this 6 6, and here it is 6 2. Then this is 7 2, and this 6 7. So let us just verify this way here. 6 6 6 2 7 2 6 7. Like in why I'm focusing on this part, it is very simple, but I'm explaining it because in book the tables are given for our better understanding. So by using this comma the replications are shown, but as it is we can't take this data to the R. So in R how we need to organize, so it will be something like this. So replication 1 up to this point, then replication 2 up to this point. Likewise it is organized. Now, to understand the structure of the data, let us see that, because those needs to be considered as a factor, and that is supposed to be number, right? So here you can see ethanol, that is considered to be a factor with the 3 levels. So 0.1, 0.2, 0.3. The ratio, it is again, let's say 14, 15, and 16, right? And this CO, that is carbon monoxide, that is 66, and whatever numbers are there, so that is given over there. Now, just to identify, I would like to add one more column over here, that is replication, so that in the analysis we can use that. So before moving to that, let us find the summary of the data. So summary and then data frame, and we can have the minimum first quartile. This is 5 parameter summary, you can say: minimum first quartile, median, mean, third quartile, and maximum. And here it is factor, so it is just giving you the count, like 0.1, how many time it is appearing, so that is 6 times. Here it is also 6 times, and here also it is 6 times. So that is what the summary of the data. Now I would like to add this one column. So I am using this replicate formula. So REP, replicate, is an inbuilt function of the R, and I'm generating this rep 1 and rep 2 each 9 times, because in one replication 9 experiments are there. So I have done that. Now if I type this repli, then what it should contain? It should contain this repli rep1 the 9 time, rep2 for the 9 time. And to append this, what I can do is I can create this new column called replication in the existing data frame, and it is supposed to be go as a factor, right? So let me run that. Now in my data frame, I can see that ethanol, ratio, and the CO, and then replication. So this is replication 1 at this point of time, up to this point of time, and then after that it is a replication 2. Now let us have some visualization of the data, because you are dealing with any type of data. The first you need to go for the cleaning, and once if it is, let's say, clean data, you should always go for the visualization of the data, because many of the insights you will get from the visualization itself. So let us prepare this box plot with reference to all the factor levels. So first what I'm doing is I'm preparing this box plot of this CO, that is carbon monoxide, and this levels of this ethanol. So here 0.1, 0.2, and 0.3. 3 levels are there, and I'm giving this color to the boxes. So maroon, green, and pink, that 3 colors I'm giving, and I'm giving the title. So let me run this. Now here you can see how it is behaving. Now in this 0.1, we are getting the consistent result, you can say, compared to this 2. And there is some, let's say less data, that is why it is not able to capture this lower limit and upper limit, and then these points are shown as an outlier here. Here you can see little more variability in point 2 output, and point 3 it is having the much more variability. So that is how this ethanol is impacting to the CO, that is carbon monoxide emission. So that is the impact of this ethanol. So let's say if you keep ethanol very less, then carbon monoxide will also will have the lesser value. So that you can conclude from this graph. Now let us do the same graphical analysis with the ratio. So here I'm taking this CO versus ratio. So we are having 14, 15, and 16. These are the three levels of the ratio. Now ratio is of air and fuel quality, or air and fuel ratio, you can say. Now here it is the reverse situation, you can say. When you are, this ratio is at 16, at that time the, CO2 emission is very less, right, compared to this 2. And when it is mentioned, when it is kept at the 14, at that time higher variability is there, as well as higher average or the median value is there. So by looking at this roughly, ultimately we are not going to, believe on this. Uh, will not go by this graphical. We are not going to take a decision. We are going to perform some full analysis. But by looking at this, what we can just understand is, so the ratio should be at 16. If let's say, less is better for the CO2 emission, जितना कम होगा उतना हमारे लिए अच्छा है. तो ratio should be at 16, and the this ethanol that is supposed to be at 0.1, then it may have a, you can say, the lesser CO emission. Now it may also have the interaction effect. So let us make the interaction plot also. But before that, let us have a look at the replication also. Ideally, replication should not be, different. So in replication 1, overall whatever result that we are getting, that ideally we are expecting when we are, replicate this once again, at the time also we are expecting the same result. So that is why we are making a box plot of it. And here you can see there is no much of a difference in, replication 1 and replication 2 output. So that is a good indication, you can say, because, in replication, if there is a change, then you need to again go for the replication to confirm which is the best, experiment, or which is the best combination. But here it is a good sign. Now let us also, find out the histogram, or prepare the histogram for this our response variable, because it is a continuous variable. And let us look at, is there any outlier, or outlier is there or not. So here also we can, see like there is no such outlier, and it seems to be normal, but we need to perform the test, right? So that we can do over there. So for that we can, perform this Shapiro-Wilk test. And here we are getting the p-value as 0.4438. That means the data is normal. You can consider this as a normal data, right? So that is what we, just perform the data visualization on this example. Now let us find out the interaction plot of this in this experiment. So here the function is interaction dot plot. That is the inbuilt function of the R. Now here we need to provide. Let me just see you what argument it is taking. So it is taking, x dot factor. So it should be factor. So this x factor, then trace factor. So that is the second factor, and the response. So this factor 1, factor 2, and the response. This 3 argument we need to give. So here I have given this 3 argument, and then type B, and then PCH. So that is what I just wanted, those point characters. So that is why I use this 18 number, 24 number, and 22 number. And then this legend, this B type, that is we are mentioning as a O. So it will be, that is the point where this is we are getting. And then color, I'm using this red, green, and blue, and then I'm giving the title to it. So let me run this. So here, since I have, increased the size, let me, do like this and then run. Still So whenever you're making the graph at that time, you need to just take care of this margins. Now here you can see, now this is what I was talking about, the point characters. So this is, this point characters are there. And this is B, that is the line that is shown over here. And here you can see on the x-axis, it is the ratio, that is 14, 15, and 16. And here on the y-axis, it is this carbon monoxide emission. And here for this, all these different lines, these colors are used, and these colors are nothing but it is represented by the ethanol level. Now, by looking at this, I would like to ask you people that is there any interaction effect with this or not? Can anyone tell me? Interaction effect है या नहीं है?
Yes, sir.
Yes, sir. It is there.
It is there. It is there, right? Yes. Yes, sir. Yes, I just have got the idea. Like आपका message अभी देखा मैंने. But when I was mentioning at the time, I realized it is 4:2 design because 4 levels are there and 2 factors are there. So I'll correct in my PPT. So yes, there is interaction effect presence in this experiment, right? So when we analyze at that time, we'll consider this as a this analysis aspect. So let me go to the R and increase again the size. Now this is the same thing I did it like by changing the this is where I put this ethanol in the color argument, and here I'm using this ratio. So that is almost the it will give you the same output. Let me just run this. It would be something like this. Sorry. Yes. So here in the previously ethanol was there as a this color of the line, but here is the ethanol is on the x-axis. So that it is also showing you the mirror image or mirror picture, because it is showing you the interaction is there in the data. Now one thing like here already we have structured design, right? So we don't need to worry about it. But let's say in case if you want to generate some factorial design based on some given condition. Now here let us take this as an example, and we want to develop let's say factorial design from this R. So how can we do that? So there is a library that is ALG design. So it may be algorithm design. So let me load that package, and here I need to mention, or I need to use this factor. I'm typing this because I can explain you in a better way. So let's say GEN, that is generate factorial. So that is the function that we are using. Now here it is asking for the levels, n variable, that is number of variable, or you can say the factors, and then center is equal to true or false that we can set, and then variable name that we can give. So here I'm using the first, let's say levels, right? So in this situation we are having two variables, and both are at the 3 levels. So I'm mentioning this 3 level and 3 level, right? And number of variable. So let me is equal to 2, and then center is equal to let's say true. Now I'll also show you by making it false, and then I'm giving the variable name. So that is ethanol, and it is AF ratio, right? Now to just make it more feasible, I'm just taking it to the second line. Now let me run this this particular function. What it is suggesting is this ethanol AF ratio, so 0, -1, and 1. That kind of thing is taken. So -1, 0, and 1. So there are 3 levels. So it is why it is taking like -1, 0, and this 1. Now if I make it false, like center is equal to false, and then if I run this, I'll be getting 1, 2, 3, that kind of thing. So that is how we can generate the design from this R, and using this ALG design package. And we can also save this and export this. So A करके एक object में save कर लिया, and then I can export it to the CSV file or the text file. Right now, that is what we just see, and then we can also use this latest package to make a chart. So let me show you quickly that. So in latest package, you can arrange likewise. So here on the y-axis, that carbon monoxide is there. Here on the this x-axis, it is on the x-axis it is ethanol, and here this 14, 15, and 16, that is nothing but the you can say A ratio, that is air to fuel ratio is there, and then it is showing you the impact of it. So you can have the idea like what is impacting in which way, right? So that is where we can use this latest package. Now let us go for analyzing the design. So we are going to use this AOV function. So that what I'm saving into the mode 1, that is model 1, and my response variable is CO2, and that is followed by ethanol plus ratio, and then the data that I'm using is stored in a DF. So that is why it is in a DF. So let me run that, and then I'll be find out the summary of this so that I can have that full view of the ANOVA. So here you can see this is showing a significant. So ratio is having the significant impact on our carbon monoxide emission. And let's say if you are looking at 0.1 significance level, then this ethanol is also having the significance impact on the carbon monoxide emission. Now we can also view this by using this model.table. We can also have the different combinations mean, right? So let us try to find out that and discuss that also. So here we are using this ethanol and ratio as a separate this factors. So grand mean is 72.83, and the ethanol, so there are 3 levels, so 0.1, 0.2, 0.3, and it is having 66.83, 75.83, and 75.83. So that is what the output, that the mean that we are getting by at this level. And for the ratio, it is 14, 15, and 16. So 78.5, 75.5, and 64.5. So that is what we are getting over here. Now it is quite similar as we discussed during the box plot, that ethanol level should be at 0.1 and this should be at 16. So that is what we have just understood from this also. But see, we have also found the interaction effect. So we can't just go or just draw our conclusion from this simple analysis, right? If there is no interaction effect, then up to this point, that is fine. But let us add that interaction effect to this. So here, to add interaction effect, you don't have to do anything. You just need to change this sign. Here in the model, I have used this plus sign when I'm mentioning this both the factor. But let's say if I am interested for the interaction effect also, at that time I have to just replace it with the star asterisk, that is multiplication sign, right? So let me use the same thing, and just by replacing this plus sign with the asterisk, and then save it into the model 2, and then find the summary. Now you can see, since it was having the interaction effect, now it is showing all these 3 are having the significant impact, right? Now again we can find out this mean, but now this mean will be also available for the interaction effect. Otherwise all these things will be same, because this is going to be same mean, right? Already we discussed. But it is also provide you this mean of this when this ethanol level is, let's say 0.1 and it is, let's say 14. So at that time, what is the emission? So that is 64. Ethanol level is, let's say this one, and it is at, let's say 15. So at that time, what is the CO emission? So that is mentioned over there. So likewise, we can use this interaction effect also. And since we have that interaction between them that we have observed through the interaction plot, so we can use that. Now let us perform some residual analysis, because ultimately we want to see that assumptions are fulfilled or not. So to plot that, we can use this plot, and then model 1 and model 2 also we are going to use. So this model 1 and in that 1, so what it will do, it will give you the residual versus fit plot, but it is slightly, you know, it is not as per our expectation, basically, we can say. And let's say if we, draw a normal QQ plot, then it is showing something like this. But let's say if whatever model that we had designed for the that interaction effect, that is model 2. So let us make that for that also. So now you can see this is, quite satisfying the condition. And here also we can, have the idea. So there are 2 points, like this is 11 number observation and second number observation, which is having some extreme value, you can say. Otherwise, it is, fulfilling this requirement. But we can also, perform the Shapiro weight test to see whether this residuals are, let's say, normal or not. Right. So if it is normal, then it is satisfying the condition. Now we can also, go for the pairwise comparison. So from the model 1, let us use this 2K HSD and then run this, and then we
Yes,
can.
sorry to interrupt. Can you show that Shapiro Wilk normality test? Because plots is not showing whether the normality is there or not.
Okay.
Thank you, thank you.
So this is the p-value that we are getting. So if let's say we are taking at 0.05 significance level, at that time we can say it is significant and the data is normal.
Okay, so it means students, when we are doing the analysis, we should be very careful. Don't look at the graph and take the decision.
Right.
Simultaneously, you should also perform the testing of hypothesis. That is what Hiren sir rightly said. Okay,
Yes.
thank you, thank you.
Yes.
Please.
Thank you, sir. Now here, let us, perform this pairwise comparison. So from the model 1, we can, straight away, that is the beauty of R, you can say, because we have saved all our analysis in model 1. And now for this 2K, I don't know how to pronounce it, 2K, or many of the time, some of the videos, they used to call it Taki. So Taki HSD, you can say in that, if I give this argument, that's mode 1, and I'm saving this in an object called pairwise, right? And then let us have a look at it, what it has stored. So here you can see the difference is, that it is, lower bound, upper bound, and then p-value. So that is also, it is storing from that model, right? So here it has basically it has done the comparison between this, let's say, ethanol and its different levels. So 0.2 and 0.1, what is the difference, so that it is showing. So here we don't find any, let's say, significant difference, and that is already we have observed in ANOVA also, right? So in model 1, ethanol was not having the significant impact, but for the ratio, you can see here this 15 and 14, 16 and 14, it is comparing between those different levels, pairs of the levels, you can say. And here this is showing you the significant, like there is a significant difference between when the level of ratio is 14 and level of ratio is at, let's say, 16. And it is also, let's say, if you are very, strictly stick to the 0.5, sorry, 0.05, at that time we have to, we can't, go for this. Otherwise it is also near to the, you can say, where you can reject the null hypothesis. Now let us perform the same thing with this model 2 also, pairwise comparison. But here it is, what it has done, it is, okay, let me just do it again. So for this ethanol and ratio, it is same as, what we discussed just now, but it is also, given this ethanol versus ratio. That is the difference it is given. So it is, taking, the interaction effect in a combination, all possible way. So you can see there are so many this interaction effects that it has considered. And now you can see the p-values of, each of the pair. So where this ethanol is at 0.2 and this is at 14, and then it compares versus 0.1 and 14, and then what is the result. So if, this is the combination versus this is the combination, so it is showing you like this. So there you can, see the p-value. So This is significant, and this is also significance, right? So likewise, we can find out the this interaction effect. So that is the conventional, we can say, factorial design, right? So we have just performed this factorial design, but let's say if we are having some blocking application into it, right? So let us have a look at the example of that. I think we have less time, so let me just quickly go through this. So this is already, I have put the snapshot of the analysis that I performed. So I'm just skipping that. Yeah. Now, if you talk about this RBD, that is randomized block design, then researchers want to investigate method of extending the life of the cut flower. So cut flower means what? When we are, cutting the flower from its plant and we are putting it to the flower vase. So when we put into the flower vase, how many days it will be fresh? So that is what it is, the experiment was all about. And the treatment factors was the liquid to fill the flower vase. And the levels are, let's say there are 4 flower vase, and then in the first treatment that they want to give is a tap water. So नल से जो पानी आता है उसी को हम भर के रखेंगे और उसमें हम ये फूल को रखते हैं, तो क्या उसकी लाइफ कितनी रहती है, राइट? सो दैट इज एज सिंपल एज दैट, हमने भर दिया. उसके बाद ये दूसरा है कि जिसमें हम एक काम करते हैं, जो नल का वाटर है उसके साथ साथ 1 स्पून ऑफ शुगर वो भी हम ऐड कर देते हैं. सो हमने वो ऐड किया. दैट इज सेकंड ट्रीटमेंट दैट वी आर गिविंग. And the tap water with 1 cup of carbonated water, that is nothing but the soda, जिसमें CO2 जो होता है वैसा water, ठीक है, उसमें हमने डाला. And the fourth is where this 7 up जो होती है, हम जो कोल्ड ड्रिंक में यूज करते हैं, पीते हैं, so उसका 1 कप नल के पानी के साथ मिला के उसमें रखते हैं, तो क्या लाइफ होती है, ठीक है. सो ये 4 ट्रीटमेंट डिफाइन किए गए. नाउ the experimental units were single flowers, and the response was the time in days until the flower wilted. The student wanted the conclusion of his study to apply too many types of flowers, so she used and randomized completely block design. The blocks were, एक तो उन्होंने रोज के ऊपर ट्राई किया, कार्नेशन के ऊपर ट्राई किया, डेजी के ऊपर ट्राई किया, एंड ट्यूलिप इसके ऊपर ट्राई किया. So these are the 4 different blocks you can consider. So these are the blocks and these are the treatments. So likewise, this analysis was, the experiment was conducted. Now let us look at the data. So all the treatments are given to, you can say, all the blocks, because it is in all the 4 treatments is there in the all the blocks. So that is why it is RBD. अगर ऐसा नहीं होता, then it might have a BIBD, जो हम next देखने वाले. So here block treatment and result is given. Now first of all we need to load the data. So that CSV file I already shared with you. So if I go and perform, then it may take a time. So I'm explaining here in the PPT itself. So वो हमने load किया, and then you can see, like, it is arranged in this particular way. Now, if we go for this data visualization, then we can use this box plot as we used just now, and then we can see like how this treatment to treatment is having the difference in the days. Now here this result is in terms of days कि कितने दिन तक वो ताजा रहता है. So you can see apparently ये लगता है कि भाई T2 जो है, that is हमने जो शुगर मिलाया है उसके साथ इसका जो days जो survive करता है, that is more compared to all other. Now this treatment 4 where we add the 7 up, so that is बहुत ही कम दिन में ये अपना जो फूल है वो मतलब मुरझा रहा है, ठीक है. सो उसके लिए हमें आगे थोड़ा एनालिसिस करते हैं, देन वी रीच अप टू सम कंक्लूजन. बट ये एनालिसिस से हमें ये एक इंडिकेशन मिलता है. नाउ लेट अस हैव अ इंटरेक्शन प्लॉट. सो दिस कार्नेशन, डेजी, रोज एंड ट्यूलिप, इंटरेक्शन है कि नहीं है? कैन एनीवन टेल मी? Yes or no?
No, sir.
No.
Okay, so there is no interaction. So accordingly we perform our analysis. Now let us, before performing ANOVA, let us check the homogeneity of variance by using a Levin's test. So Levin's test is from the low state package. From that we are using this, and this result with reference to the treatment, whether it is same or not. So here it is fulfilling that condition. So we can say the variance among all these treatments is equal, right? So that is satisfying the condition. So we can move ahead with our analysis. Now here also, what we have done is we have used this AOV formula. So AOV the analysis of variance function, and this result is a function of treatment plus block. Now why are we are using this plus? Because there is no interaction effect. So we are using this plus sign, and then we are providing the reference of the data, and then we are seeing the summary of this model. So here you can see this treatment is having the significant impact, right, on this result, or you can say the day survive, right. उसके ऊपर ट्रीटमेंट का सिग्निफिकेंट इम्पैक्ट है, ब्लॉक का सिग्निफिकेंट इम्पैक्ट नहीं है, ऐसा हम बोल सकते हैं इससे. But let us have a look at it in a different way. Let us go for the pairwise comparison, because ultimately we want to see like which treatment is having the higher effect, or which treatment is having the lower effect. So again we are using this Taki HSD, and then we are providing this model. And now here which argument I am giving, because from this model we would like to give this treatment. So first of all we would like to do pairwise comparison of this treatment. So what it will do, it will go into the model and find out this treatment related attributes and then do the analysis. Now here what it has done, it has compared this T1 with T2 with T1, T3 with T1, and T4 with T1. Then T3 with T2, T4 with T2, and then T4 with T3. Likewise, it is done the comparison. Now here you can see these are having this particular three pairs. They are having the p-value less than 0.05. That means what? That is significant difference between this T4 and T1, T3 and T2, and T4 and T2. Now, by looking at difference, we can conclude that which is favorable situation, which is giving you the most result. So here in this case, we can assume that this T2, not T2. Okay, so T4 is the worst, right? Because it is coming in a negative. So T4 is a worst treatment, you can say, among all these four. Here also compared to this T3, T2 is best, because it is also in a negative in comparison of this T3. Now to have a better idea what we can do, we can either find the mean of each as we use this models.tables, and in that we have used the mean, or we can go to the box plot and find out the best treatment. So in that we have already discussed that T2, that is with sugar, was giving the best result. Now here, let's say whatever we have discussed here, let us present it in a graphical form. So here you can see we just need to use this plot argument and then pairwise treatments, because I've saved this in a pairwise treatment. So I'm just giving this object into this, and I'm giving this color. Color is just to distinguish between these lines. So this is significant because it is not intersecting with the 0. This is second, and this is third. So that is same as what we discussed in this slide. So T1 and T4, T3 and T2, and T4 and T2. So it is the same this one. So these are the treatments which are significantly different, that we can say. Now, in the analysis we have found that there is no impact of block, right? So block to block variation is not that much. So let us have a comparison of that also. But here we are not getting any p-value which is less than 0.05, and in this pairwise plot also we are not getting this any of the combination which is not intersecting the 0. So we can say that it is a significant. So block is not having any impact. So the treatment 2 is equally performing on all type of flower that we can compute, because here our block was flowers, different types of flowers. And let us perform the residual analysis. So QQ norm and QQ line that we have just performed on this residuals. And you can see again, as just now, sir has mentioned. So these are 2 points that we are, seeing that it may have out of the range. So we can perform that Shapiro test on this residual and be assured, right? So we have also, used that Shapiro test, and we have observed that the p-value is 0.1608. So that means the residuals are following a normal distribution. Yes. Uh, okay. Do we have time, sir? Shall I continue with this?
You have a last 15 minutes.
Okay, fine, fine. So we'll wind up.
Madam, is it fine? Jyoti madam?
I'm okay. Yeah.
Okay,
Okay,
okay.
okay.
So,
Student should be also.
And one more thing, Hiren, in the last session, Madam has already written in the chat box that
okay,
whenever you have a such situation, we should go for the ranking of a treatment. So Madam
okay,
has
okay,
written that T4 is the worst because which has the minimum time of survival and
okay,
maximum time of survival is to the T2.
okay, okay.
So
So that,
that is also the one of the beautiful way to decide, and that is how there are the tests are developed order alternative.
okay.
Alternatives are order.
Hmm, hmm, hmm,
John
hmm.
Kerry test and other tests are there. Anyhow, please continue.
Okay, okay, sir. So now, this is already we have discussed like intuition of this BIBD. Now let us see the example of it. So an engineer wants to improve the yield of chemical process. The treatment factor of interest is four different chemical formulation, that is A, B, C, and D. Now batches of raw material is considered to be a block, and there are four levels, right? So block is also having the four levels. Now there is that means you can say there is a four blocks you're having, but there is a shortage of raw material because this is the practical constraint कि भाई हमारे पास इतना raw material नहीं है कि हम like all four experiments में हम conduct कर पाए, ठीक है? So only three chemical formulations can be accommodated with that raw material, and we have to use suitable design to conduct the experiment. So if you look at the data, then here the chemical process or the formulation, you can say A, B, C, D. And then here batches of raw material is 1, 2, 3, and 4. But in each of the, this block, we can't apply all this four treatment. So that is why randomly it is assigned. But if you look at the, A, so A treatment, how many time it is repeating? So 1, 2, and 3. This is also three times. This is also three times. This is also three times. And that is why it is called as a balanced incomplete. It is incomplete, but it is balanced, right? So in that way, we can say it is a case of a BIBD. Now, if we perform this, analysis using R, then this file I already shared, chemical BIBD.csv. The formulation is shown by A, B, C, D. So that is in this column. Raw material 1, 2, 3, and 4. That is the block for us. And then the yield that is given in the yield column. Now let us have a data visualization. So first of all, we'll make the box plot. Now here, by looking at this box plot, we can see like, there is a there may be a significant difference between this and this, and it may be this and this also. But there is least significant difference between this A and D. But that we can, only know by performing some uh, proper, let's say, ANOVA technique, right? Now let us make the interaction plot, but it will be, very weird interaction plot. See, so very difficult to conclude from this. Why? Because this it is incomplete block design. So that is why this statements that will not repeating in all the blocks. So that is why you might have this kind of interaction plot. Now, before moving ahead, as just we have seen in the last part, we have to check the homogeneity of variance by performing the Levin's test. So we have performed the Levin test that, is there, the variance of all this formulation A, B, C, and D. So is it same or it is different? So here we are finding that it is a same across all the formulations with reference to the yield. Now it is a green signal that we should go for the ANOVA. Now here we are using again the same function AOV yield, that is followed by, or the you can say it is a function of formulation plus raw material. Now, please remember that sequence is also important as far as I was just referring to some of the books and article and the videos. If you write this RM first plus formulation, then also it will give you the output. But here our treatments are this formulation, right? So we always write down treatment first and then our block. So whenever we are typing it down, because software will give you the output. इसको इधर रखेंगे तो भी output देगा, but it may change all this calculations and the significance level. And then if you find out the summary, then here it is also showing that this formulation, it is having the significant impact. So on the yield we can say, but raw material, that is not having the significant difference. Like this block is not having the impact, as we just seen in the last part or the last example. Now if we go for the pairwise comparison, so again we are using the same this thing, and here we can find out that where it is significantly different. So these are the pairs. So whatever we feel during the box plot analysis, it is giving you the same result. Like there is a significant difference between B and A. Here it is a significant difference between C and A. Now for A and D there is no like significant difference, right? So that is why P value is very high. But here again, with this B and C, both are having the significant differences. Now if you want to visualize this in this pairwise comparison in this visualization plot, then we can use this plot dot into bracket this pairwise, and then you can see here D and C, it is having the significant difference. D and B, significant difference because it is not intersecting with the 0, but this are intersecting with the 0, so that is why there is no significant difference in those pairs. That is what we can conclude. Now, we can also use this DAE WR package. So to, perform this BIB test, so that, we can find out the means and everything in a single command. So we can load this library and then we can use this BIB.test. It is a case sensitive. So BIB is in a capital and then test is in a small. So BIB.test, and then we have to give this block, formulation and the yield. So here the sequence is something like this: block, treatment and output. And that is output I am saving it on the A object, and let us print this A object. So it will give you so many output. Now the first is parameters, so lambda value, then this treatments, then this block size. Total 4 blocks are there, replication, and then alpha level and test BIB. So that is just information that it is giving. Another output that it is suggesting is with reference to the mean. So here, with reference to all these treatments and the yield, you can see this column is important for us. So here you can see this C is giving us the best yield, the treatment C. So 116.33, which is highest among all these things. And in pairwise comparison, we have also seen that it is significantly different than the other, right? Then what are the groups it is making? So that is also taken from the past analysis, because here we have used this package, so it is showing in its designed pattern. So let's say this B and C, that is making one group, and this D and A, that is making another group. Now quickly let me go to this box plot. Yeah, so here also we can see the same thing, that this is making one group with reference to this yield, right? So here clear cut line we can draw. So this is group A, this is group B. And that is the same thing which is displayed in this BIB.test analysis. So we are getting the same thing. Right? So that is how we can perform this BIB test analysis, and there are also several other packages that we can do. We can use that packages. There's Agricol and some other packages are also available. So here we can say the treatment treatment C is giving us the best result. So we should replicate that. And once it is replicated and it is giving us the best result, then we can say this is the best treatment to go about. Now to optimize it, we can also go for the response surface and all, but due to time constraint, we have covered up to this point. And these are some of the reference from where I taken some of the examples and the material. So this is the book, very good book, and then this Montgomery book, and these are the links that you can visit. So thank you so much everyone for being patient. I was out of time, then also you were there to listen me. So thank you so much. Yes.
Yes. Any questions? Anyone? Hiren sir, madam has written some comments. Please go through it.
Okay, okay. One shot analysis in R. MSc students try
It is for
BIBD.
MSc students. They
Okay.
always want shortcuts. So this is the shortcut they learn.
Yes,
So
yes.
entire design in a 1.5 hour. That is the shortcut, madam.
No, 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 no. Design is very, very vast subject. ये तो सिर्फ मतलब छोटा सा portion था, बाकी ये design तो बहुत बड़ा subject है.
Yes. Any questions? Anyone? See, see your MSc exam is also near, and design of experiment is one of the paper. So if you have any questions related to the topics, especially RBD, BIBD, and the factorial experiment, and how to analyze through R. So please, you may ask the questions. Feel free.
I have also shared one link of link to download this material in the chat box. So you can also have the same uh, PPT and this files that I was using, that R code file, so that you can have.
Yes, madam. Jyoti, madam. Please, any comments, anything else?
Yeah, according to me, beautifully presented. Design of experiment is a very beautiful subject, although people keep away from it for some reasons. I don't know. Maybe it does ask a bit high level of logical thinking or logical
Right,
ability, because you need to visualize, as rightly Hiren said in the beginning. You need to visualize what is replication, what is randomization, what is blocking, and once you are in that, in your mind visualized picture, then you enjoy it.
right, right. Correct, madam.
Yeah, but students can learn how to present, how to prepare, and how to think.
Yes, yes,
Yeah, if any questions, please ask, and then you can proceed.
yes. And I'm also sharing one link. जैसे हम certificate देते हैं तो उसका link मैं दे रहा हूँ. But certificate will not be generated immediately due to some technical problems. So within 2 days you will receive your certificate. So please fill out this form to claim your certificate. तो वो भी मैंने chat box में डाल दिया है. और इसका recording जो है that also will upload on the channel, so you can also view later on.
Yes, sir. Any questions from student side? I hope everyone is awake.
So,
Yes,
I
Yes,
am.
sir.
Okay. So
Everyone,
Sanjay is also
okay.
there.
Hiren
Yes, sir.
sir,
I'm there.
Good, good.
Yes, yes, yes. Loknath ji.
yeah, sir, actually, can you give a brief about the resolution? You have covered all the topic, only resolution left out. So, can you give some limelight in that?
Uh, Resolution. I just need to check it, once, because I have just prepared for this only. So I'll not misguide you because I need to just refer it again. Because since long back I have, left the grip on this subject.
No, as sir and ma'am told, you have covered everything. Only resolution left out. Just have some doubt in that. That's why I asked. No problem. No problem.
I'll come back to you. Not an issue. I'll just see it. I'll just check it out, and then I'll come back to you.
Fine. Fine. Thank you. Thank you.
It is associated with the confounding, but of course, you have also, I think, studied the concept of resolution in the second semester, or it is in the third semester.
Sir, in third semester.
Okay, so I think the topic is covered by madam.
Yes, sir.
Okay, so madam, can you throw some light about the resolution? While if you
See,
yeah.
resolution is related to factorial design. That in factorial design, if you want to cut some of the runs or some of the factor level combinations, like in today's this webinar, we saw there was an example of three square design, where there were two factors, each at 3 levels. And suppose you want to reduce the number of runs. There were 9 runs, but you want to reduce it. Then what you do? So you have to do it very technically. Technically in the sense, you shouldn't lose too much on your factorial effect estimates. So resolution concepts are given with respect to that.
Okay, ma'am. Thank you, ma'am.
Okay. Yes, I hope everyone has filled up the form. Anyone left to download the materials and fill up the form?
Yes, sir. Unfortunately, I was left from the meeting, sir, so I not got the link.
So, so
Yes, I'm pasting
yes,
it
please
again.
share the link again.
Yes,
So
sir.
the
Thank
first
you, sir.
thing that is material, and then another link that is for the claiming the certificate.
Thank you, sir.
Yes, the person who will fill up the form, they will get the certificate. So make sure that you should fill up that form.
Hiran sir.
Yeah, Jaiswal, please.
Yes.
Yes, I have a doubt in sir RBD. There is a code written and there is a hashtag and all that. I didn't understand that
Okay.
in RBD part, sir.
Okay. Actually, hashtag is used only for the comment. That is not the part of code. Let
No,
me
sir.
just tell you.
Sir, which is in the code. That's why I didn't get that.
Okay. Let me just share my screen again.
Some no. Yes. Yes, sir. Yes, this one. Column
Yeah.
back.
Uh, this one.
No, sir. Afterwards, column. That's yes, sir. This one.
This one. Okay. So here, let me
Yes, sir.
just explain you the code. So here, this is just a comment that if you see my R code file, then all the sections
No,
like
he is saying in the box plot there
Column.
is a column. Yes, yes.
acha, this one.
What it means?
Column, sir. Yes.
Okay,
This
okay,
one.
okay. This is color actually. So this is basically a color argument.
I didn't get that.
Okay,
Sir.
okay. Let me explain you. This is color argument.
Okay.
It is not column argument. It is color argument. So if I write it, let's say red over here, then all these boxes will be filled by the red color. Okay. So here I have mentioned this hexadecimal number. It is called as a hexa number. for the color. So each of the color are having their code basically. So different shade. For example, if I change this 87 to 88, then this slight shade of this color will be changed. Now, why I choose this color is because it is matching with our logo. This first bar of our logo, that is the color.
Okay. Okay, sir. Okay, sir.
Is that color?
Okay, okay. 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 Okay, sir. Thank you, sir. Got it, sir.
Okay, I'll like to answer in different way to Loknath. Hello, Loknath.
Yes, ma'am. Yes, ma'am. I'm here, ma'am.
Yeah, what is your aim? How much score you want for exam? After exam?
Ma'am, definitely would like to score much, ma'am.
Like what?
Uh,
Tell in
first
range
above 60%.
above 60%. Okay.
Yes, ma'am.
So if I say there are 3 classes, pass class, then second class, and say above 60, that is first class. Okay.
Yes, ma'am. Yes, ma'am.
Yeah. So then pass class is resolution 3.
Yes, ma'am.
Okay. Second class is resolution
Yes, ma'am.
4. And what is
Yes,
your
ma'am.
final? Like industrialists want what? All main effects and all two-factor
Yes, ma'am.
interactions. Okay.
Yes,
So
ma'am.
that is
Yes, ma'am.
resolution 5. So what you are expecting is resolution 5 result. Okay. So your
Yes, ma'am.
preparation should be
Yes,
accordingly.
yes, ma'am.
Okay, Tanaji has shared his views that he is looking for one more webinar on the design of experiment, especially response surface methodology.
Okay. So we'll plan and definitely let you know when these dates will be there. But most probably it will be after Diwali because I think your exam schedule is also there and all. So
Tanaji has already cleared MSc examination. Is
Sanaji
it?
is our now alumni. Actually,
okay.
we want to design RSM webinar for actually industrial professional also. We'll
Okay.
do it. We'll do it.
Definitely.
Okay, I hope everyone has filled up the form, downloaded the materials, and if no more questions, madam,
Yes,
then
sir.
should we stop our
Yeah,
webinar over here?
yeah, we can.
Okay, with kind permission of our HOD, we will say the end of this webinar, and on behalf of the Head Department of Statistics, and the entire the student association, I would like to thank Mr. Hiren Kakkar, CEO and the co-founder, for giving the beautiful presentation on the design of experiment using the R. And we wish some more topics in the near future. So once again, thanking you. And in advance, happy Diwali and prosperous New Year to all of you.
Thank you,
Thank you
sir.
very
Same
much.
to them.
Thank you, sir. Same to you, sir.
Thank you, sir.
Thank you, sir.
Happy
Same to you,
Diwali
sir.
to everyone.
Happy Diwali. Happy Diwali. So please, everyone has to leave the meet. Thank you.
Thank you, sir.
Thank you so much, sir. Thank you, sir.
Thank you, sir.
Thank you, sir and ma'am.
Yeah.
Hello.
हाँ बोलो धर्मेश બસ બધા લીવ કરે
Hello.
બંધ કરો
ના એટલે બસ આ રિમૂવ કરવા પડશે સંજય નું છે અને
સર હું છું હજુ સર લાઈવ
ના પણ આ એ તમે અલગ મીટમાં